Hello, and thank you for taking the time to listen to my presentation. I'm going to share about the project that I did, which was about modeling many-body interatomic potentials using graph neural networks. Now, I imagine most of you probably don't have background with interatomic potentials, so I'll explain a little bit about what those are now. Essentially, when you create a simulation of atoms, your interatomic potential is something that measures the potential energy of those atoms. And after the interatomic potential measures that potential energy, the energy is used to calculate velocities and forces, and then essentially propagate the simulation forward in time. So this is what a pairwise interatomic potential looks like, the simplest form of interatomic potential. This demonstrates the uh, potential energy of an atom as it is certain distances away from other atoms. And as you can see, the happiest spot for the atom to be is down at the very bottom, right down there, of the interatomic potential. That is at the equilibrium bond length. So this is a relatively simple form of an interatomic potential that just takes two atoms and then says what's their potential energy. And then it can calculate those for all those atoms. But there's actually two different types. This is a pairwise interatomic potential, but there's other types of interatomic potentials called many-body interatomic potentials. Those have two parts to them. They have this relatively simple pairwise part, which is still a complex function, and then they have an even more complex part where they might generate what an electronic field around the atoms would look like, and then calculate the amount of energy it would take to embed an atom inside of that electric field. So these many body simulations can be quite time consuming. And again, the functions that they use are quite complex. And since machine learning can often result in time savings, I asked the question, can we approximate this behavior using a graph neural network? The interesting question is graph neural networks themselves have an inherently pairwise behavior, but graph neural networks can also take into account messages from neighbors of neighbors, and the nonlinearity in the potential itself can potentially help take into account some of these many body effects. So to create this data was a relatively complicated problem. I first grabbed an interatomic potential. It was an EAM potential um, from Mission and collaborators. And essentially an EAM potential is a many-body potential that consists of these pairwise and embedding terms. The simulation itself to generate the training trajectories and testing trajectories was performed in LAMMPS. And each of these simulations is 1 picosecond of atomic motion. Now, that doesn't seem like very much, but just creating 1 picosecond of atomic motion took 15 seconds of actual simulation time. And as you can imagine, this blows up as those get larger. The training was done with a training set of 172 atoms, and I wanted to know if we train on 172 atoms, can we extrapolate and test it with a larger system? Can this graph neural network with a small system of training learn behaviors that will help it model a larger system accurately? Any visualizations we see were done in a software called Oviedo, and you can see some of these here. These are little animations of essentially what it looks like as you simulate these. The top is the training data, and then the bottom is the testing data that I'm using. So initially, I generated a model. The biggest problem is that it's a long simulation and there are lots of atoms in these models. And each atom itself has 7 input features, which include its mass, all of the X, Y, and Z position, as well as the X, Y, and Z velocities, which are all generated on each time step. And then there is a neural network that is used to approximate the forces on those atoms. These neural networks consist of a message network and an update network, I'll call them. Each had 3 hidden layers with ReLU activations. The hidden layers themselves had a width of 20, and then the message that was passed between atoms had a dimension of 10, so 10 elements. Um, Ultimately, these were not so much optimized hyperparameters so much as they were constraints of model size. The larger those parameters got, the better the model performed, but eventually the model was unable to fit within the GPU of on Google Colab. So that was a limiting factor there. And then each of these training iterations was run for 100 epochs on the testing data, on the training data. And as you can see here, the original simulation did not go so well. It seems to be severely overfitting. And then you can see even on the training data, there is some very, very non-physical things happening. It's basically just exploding. So that's not optimal. And so I looked for ways that maybe we could improve that. And specifically, I wanted to work on simultaneously improving the training performance and also improving that overfitting that we were seeing. So tried some things, as much hyperparameter tuning as I could do. And then eventually I worked out that adding dropout layers into the network was very effective at improving the performance. As you can see, these simulations here, while not perfect, have a lot more physical likeness to them. It looks like the metal might be melting a little bit, but at least atoms aren't flying all over the place. And as you can see from the training and testing data here, it's no longer overfitting. And in fact, the loss is getting quite low, but the loss does level off at about 0.1 using MSE loss. So that's not optimal. And so I made a few more attempts to adjust that model to account for those things. The first thing I wondered is, well, we're taking the XYZ positions and XYZ velocities, but hypothetically, the distance between those atoms should be enough in those messages to gain some semblance of an approximation of what's happening. This makes it more of a pairwise potential, but I wanted to know how good does it do? And looking at the loss, it seems like it does relatively well. It seems to train and not overfit very much. But when we actually looked at the simulation, this is on the testing data, you can see once again, some very non-physical things are happening there. So ultimately simplifying it down to distance instead of taking into account all the positions, it crippled the model a little bit. I also attempted to change to an L1 loss instead of an MSE loss to drive all the terms to zero, as we had done in the previous graph neural network homework assignment. And that worked okay, but the training still was not as good as it was in the case of the MSE loss, and the simulation results bore that out as well. So in terms of computational time, did we get those time savings we were hoping for? And the answer is almost, right? On the simpler network with dropout, the one that performed the best, it took 22.5 seconds to run a simulation of 1,000 time steps, 1 picosecond. And the baseline time for lamps was 15.79 seconds. So it's comparable, and perhaps with some improvements in architecture, smaller layers, you could get it below that lamps time, but you lose some in terms of accuracy of your model. I thought the distance network might be better because it has less parameters, but the complex distance calculation ended up making it so it was a lot slower, almost 10 times as slow as the LAMPS simulation. So why did this happen? How could these be better? Well, one known problem is that machine learning interatomic potentials can produce non-physical results. One of the reasons is it can be difficult to extrapolate to large simulations. And another could be that it is hard to generate training data that's outside of reasonable bond lengths. All of the atoms that I trained on were vibrating at their regular bond lengths, but interatomic potentials are highly dependent on the idea that if atoms get really close, they should push each other away very strongly. So you're unable to model that using the training data that I had. Some potential solutions could be including some of that in training data, maybe by having higher temperature training data, and then trying to run low temperature simulations. Also, dynamically updating the adjacency matrix instead of just setting it at the beginning could be helpful as atoms potentially get closer to other atoms and shift their neighbors slightly. And then one other thing that I wanted to do but ran out of time to do was to use the same simulation scheme and integration scheme as LAMPS, which is the velocity relay integration. But the conclusion based on this is that GNNs can approximate some many-body effects, and they do better if you take into account all positions and allow for those many-body effects instead of just distances. But the one I created has not yet exceeded the speed and capability of an interatomic potential. Thank you so much for listening to my presentation.